Okay. And then we can start the afternoon session, and we are very happy to have Katrina Barron, who will talk to us about number theory arising in conformal. Don't look surprised when I make your title.
You look surprised. Right, so we talked a lot about modular tensor categories, and I just wanted to give some motivation as to why one might expect modularity properties to arise naturally from conformal field theory, just from the worldsheet geometry. So that's kind of just a simplistic goal of the talk, and to think about why they would. You know, a lot of times we talk about rational, nice conformal field theories, but one of the motivations I want to give is that we should expect at least some nice transformation properties anytime you have a VOA. I will be talking mainly in the VOA setting with just one module instead of intertwiners and correlation functions with more than one module, just because the theory gets a little bit more complicated in terms of the geometry that you have to use if I go outside of that. But you can ask questions about that. Okay, so the point here is that I'm just going to give you the backstory in case you're not familiar with the VOA setting. For me, a VOA, the main thing I want is Z-graded vector space of particle states graded by energy, usually an Laplacian or an L0 operator I'll get to. I want each one of these spaces to be finite, although we don't always need that. But at first, we're going to assume that. And with this, as hopefully I'll motivate later, you will naturally have, if one has a vertex operator algebra, which for me is a graded algebra whose algebraic structure is governed by worldsheets, propagating strings in conformal field theory. Then one naturally has, because the worldsheet by Wick rotate and everything, we're doing the chiral side, the conformal structure. You have a conformal differential geometric structure on that worldsheet we'll see. And those infinitesimals give you a representation of the Virasoro algebra, a central extension of the Witt algebra of vector fields on the circle from your differential geometric study. So just for right now, though, let's just concentrate that this I can't even see the dot. This vector space has a representation of the Virasoro algebra, and this grading that I'm given is in terms of these are eigenspaces for the L0 operator for this. Okay, I'll write my fields as a Laurent series expansion. And this weight grading that I have, if I'm acting by one of these modes, the way it's set up is that I'll either raise or lower the mode that I'm acting on in this module, in this algebra. Okay, because I have these finite dimensional weight spaces, I can write down something called the graded dimension. It's shifted a little bit by this central charge term, okay? Or more generally, I could take any one of these operators that is weight preserving. So a certain one of these, if I put it into this formula, doesn't raise or lower, it's grade preserving. So if I restrict it to one of my finite weight spaces, then I can just take, oh, there's a missing trace here. There should be a trace. It should say trace right there. I can take the trace of that. Hence the term trace. I can take the trace of this operator acting on there. So these are in general called the 1-point traces, if you will. Okay. Thus, if I just took the vacuum whose 0 mode is just the identity, then this graded dimension would just be what was called the 0-point function or the vacuum graded trace. Okay. So for instance, let's just take one free boson. All you got to know about this as a VOA person is that it is isomorphic as a vector space to just polynomials in an infinite number of variables. This is the bosonic state, just the ground state, excited, excited, excited. Okay, the weight of this thing, my L0 operator happens to be 1/2 x2 squared. You do the actual VOA structure, then the L0 part will act on this, and this will be the weight. So we naturally get something that is familiar to a number theorist, and that's that the graded trace of each weight space is just the number of partitions of n, right? These are the non-negative integer partitions of n, and I get the Dedekind function. If I take, so one of the most common constructions of a VOA and a nice VOA is if I take a positive even lattice. This is another nice VOA. You already know a lot about VOA theory. If you know bosons, just one free boson, and you know the group algebra of the lattice may be twisted in terms of its multiplication, and this is the vector space that will give you a lattice VOA. And there's all sorts of thoughts among VOA people that most VOAs are somehow related to a lattice theory. So then you know a lot, and you can write down the graded dimension, and you have this function. These functions I'm writing down that I'm naturally getting out of the most basic VOAs that we know about have modularity properties. So if I take the modular group, and I act by Mobius transformations, then we call this a modular form of weight K, and it transforms like this and has some nice properties at infinity. So for instance, for the boson, this graded dimension is a modular form of weight -1/2. The lattice VOA is a modular form of rank of weight, the rank of the lattice over 2. So you're naturally getting this modularity properties out. And this is a famous story. And then there's, you know, Monstrous Moonshine and blah, 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 that these have wonderful properties. Okay, this was the graded trace or the vacuum trace and other traces of the VOA itself. I can take a module, and if I have a nice module, so a lot of times we'll call something an admissible module. You know, so you're trying to gather together some collection of modules that hang together nicely, that are closed under the tensor product, and make a nice category. Maybe it has modular proper, it's a modular tensor category if one's happy. Okay, so for me, for most of this talk, we're just going to talk about admissible modules, meaning that they are positive Z gradable. So they have a weight space grading as well with respect to this L0 operator, but in general, I might have generalized eigenspaces and not just eigenspaces. Okay, but these operators still raise and lower as you would, and usually I have a nice correspondence between these two different gradings. But that's what I'm going to mean by admissible. And then I can again form these graded traces. I was successful in putting my little trace there. So I take one of my 0 modes, something that's not raising or lowering, and the trace is now well defined on these finite dimensional spaces because I've required that. And I have these 1-point trace functions. Okay, or more generally, I could put it in point function.
So is there any relation between L and lambda?
Yes, lambda is the L0 weight.
I mean, on the previous slide,
Yeah.
there were 2 gradients, y by integer L and the other by complex lambda. So,
right, the admissible just means that I do have a positive n grading. So I don't have too many, I don't have an infinite number of these conformal weights so that I don't have a bottom level. I just have it's a positive energy module. It's a positive energy module, and it's graded. It has these the spectrum of L0 acting on here. Okay, so the first result of the connection between number theory and these graded traces and stuff came from Zhu, and in the specific setting of if V is rational, meaning it has semi-simple representation theory. So every module decomposes completely into irreducibles, and it only has a finite number of simples. So there's a C2 cofinite condition. It just means that I have this space, and if I mod out by my V by this space, then this is a finite dimensional space. And the reason that the upshot of that is that you only have a finite number of simple modules, because there's this algebra running around called the Jou algebra, or the zero mode algebra, that it acts as, for instance, the universal enveloping algebra for your Lie algebra, or the group algebra for your finite group. So it tells you information, it contains all the information about the simples in this case. And it's bounded by this, so then you only have a finite number of simple modules. This is the nicest category, and you'll hear this a lot, that, you know, if we know that we have a rational C2 cofinite VOA, then it will form a modular tensor category via the construction of Wang. Okay, and this started, this fact of it having nice modular transformation properties and a nice S matrix and satisfying the Verlinde formula, started with Jou's 1996 theorem, in which he proved that these graded traces, or partition functions, if you will, are, the space of them is modular invariant. So any given one might not be invariant, unless you have something very, very nice like the moonshine module. But the space of them, the action of SL2Z, will preserve that space of formal Q series. Okay. And in this case, your L0, your eigenspaces, your generalized eigenspaces for your modules are all in fact eigenspaces. They're all ordinary modules, if you will. Okay, I just want to focus on the specific things that allows you, that are the ingredients in Jou's theorem, and I want to see where we could expand this. So the big things that you need about your functions, so the fancy thing about graded traces is that they're symmetric. If I do the modes of two vertex operators and I switch them, then I get the same Q series, they're linear, and they satisfy this logarithmic derivative property. So it says that if I take the zero mode here, this is just L0, the zero mode of omega, and I act here, then I get this logarithmic derivative out, i.e. I get a derivative with respect to tau if I think of Q as e to the 2 pi I tau. I guess I didn't write that here, but see, you know, like so far Q has just been this formal variable, but if I think of it as e to the 2 pi I tau, then this would be a derivative with respect to tau, so a logarithmic derivative. Okay. And the proof of Jou's theorem uses the main guts of it that I want to focus on, I'll say, other than this finite stuff, is that it uses the symmetry, linearity, and the logarithmic derivative property of these functions, these graded traces that we have. Then it uses Jou reduction. And Jou reduction is just a property that is going to exist for any VOA, for any abelian intertwining algebra. And this is the use of a change of variables from on the world sheet, from the disk to the cylinder, and the associativity and commutativity properties of vertex operator algebras, of vertex operators, or intertwiners. Okay, and that's the geometry I'll just talk about. And then Jou's theorem itself just uses the fact that this zero mode algebra does give you this correspondence between the simple algebra, the simple modules for this algebra, which is finite dimensional, and the simple admissible V modules. And the fact that this functor going from here to here is a certain type of induction functor. Okay. Can you extend this? So these VOAs, they're very, very nice and everything, but can you extend this? So Miyamoto in 2004 extended this picture to say, okay, maybe you still have C2 cofinite. So you have a finite number of simples, but now you have indecomposable non-simple modules, indecomposable reducibles. This is the setting of logarithmic conformal field theory. And he said he had realized that, as was known, the graded traces were not enough to preserve modular invariance. You needed these gadgets called graded pseudo-traces. But if you add those in, one still has modularity. Okay, one of the problems is that C2 cofinite irrational VOAs are very, very hard to find. We can't find them. There's only a few that have been constructed and well studied, as one saw last week, in particular for Thomas's talks and things like this. Okay. Okay, and the C2 cofinite not irrational. So now you have in general, you may have your L0 in particular not be diagonalizable. So you might have generalized eigenspaces that are not eigenspaces. That's not necessarily true of all logarithmic modules, but and you get these logarithms. Well, I'm going to get what's called a naked tau appearing in pseudo-traces and or intertwining relations. And thus I must have a general logarithmic term. Okay, so how do you, if one can't get one's hands on C2 cofinite irrational ones, can you extend this further? And so recently, a group of us has shown that one can go outside of the C2 cofinite setting and have a well-defined notion of graded pseudo-traces. And if they maybe don't have modular properties, they have what are called quasi-modular properties. They're just off from being modular. Okay, examples in our setting that we can understand are all indecomposable modules for the Heisenberg VOA. We also have certain settings for the universal Virasoro VOA for certain central charges. And here we are just inducing from the level 0 Jou algebra, but for those, but we do have some modules that admit well-defined graded pseudo-traces. Okay, in both the Miyamoto setting and our setting, what is the proof of these modularity properties? So the proof involves the fact that our graded pseudo-traces in all these cases are symmetric, linear, and they satisfy the logarithmic derivative property. In fact, if I have any kind of function that satisfies these stuff, I can proceed to 2 and 3 and ask interesting questions about functions that arise. Because I always have this change of variables, which is just a world sheet change of variables. I always have this associative and commutativity properties, which I'm going to talk about later. In general, once one goes into the indecomposable non-semi-simple setting, into the logarithmic conformal field theory, so we said that the level 0 Jou algebra, this guy, this is just a coset space of your B. So it is something that you can just look at B and C. These guys will govern your simples. It'll tell you what all the irreducibles are, and it will tell you any irreducible that is induced, whatever that means, at level 0, meaning that if there was a Jordan block of size 2 or bigger, then it would appear at the 0 level. So you put in your Jou algebra module in the vacuum level, and then you raise from there. You just take all your raising operators and you act from there, basically as induction, this induction functor. So if I have a setting in which any increase in size of Jordan block on my module occurs at level n, is there's an algebra, there are these things called higher level Jou algebras that insert a module for the higher level Jou algebra at level n, and you induce from there up and down. You only need to look at the level in Jou algebras if you're looking at modules that have an increase in Jordan block size at level n. So we got, you're lucky if you're dealing with the Heisenberg, it turns out, and I can go, depending on what people want to hear, for the Heisenberg, it so happens that its level 0 Lie algebra doesn't just tell you everything about the irreducibles, the simples, reducibles, it tells you everything about the indecomposables as well. For other situations like the Virasoro algebra, I can induce from a larger Jordan block size for its level 0 Lie algebra as well, and then I can study those. But it will necessarily have indecomposable modules that have an increase in Jordan block size above level 0. And so these are much harder to deal with. Okay, so we kind of skirt meeting these higher level Lie algebras in these examples. This paper is on the archive that has the examples. It's being rewritten, some of it, but the examples are still the same. Okay, what are graded pseudo-traces? We've heard about graded pseudo-traces. Okay, need some definitions. So basically, if one has a weakly interlocked module, so A is just any associative algebra, I'm thinking of it as the Lie algebra though. I take the SOCL, if I have just irreducible SOCL, and usually in these cases, then I have a unique maximal subalgebra, and we call it weakly interlocked if U mod the SOCL is isomorphic to the radical and U mod the radical is isomorphic to the SOCL. One of these almost always happens, and one of them is harder for this to happen. So if I had this situation and I can think of the same, we can just say the same words, it's just now instead of an algebra, I'm letting this be a VOA, and I have a admissible indecomposable module, and I'll call it interlocked if it has the same property. Okay, just for a very good concrete example, let's take this guy. So here are all the indecomposable non-simple. If J is not 1, J is 1, then those are your simples. We're just doing finitely generated modules over PDE. And UK is always weakly interlocked. If I take UK, then the SOCL is just U1, the radical is UK minus 1. So here's your nice example. I have the X is acting by this Jordan block. And the nice thing about this, the fun fact, is that this algebra is the Lie algebra for the Heisenberg and for the universal BOA. These are obviously not C2 cofinite, right? This algebra is not finite dimensional. There's an infinite number of irreducibles, but it's something called C1 cofinite. And so kind of pushing the envelope, from very nice VOAs that were C2 cofinite and rational to C2 cofinite and irrational, one can push to, and then one of the next natural things to look at is C1 cofinite. And so we're in that setting. And the point is that I have this stabilized linear operator that's acting on the SOCL. I have a stabilized linear operator acting on the module mod the SOCL, this radical part, and these two are the same things because this is interlocked, they're isomorphic. I guess I should be up here with we're just regular algebra. And this Jordan block is unique up to change of variables, right? Just a rescaling. So that means that this off, so what am I trying to do? So the traces tell me about what's going on the diagonal, right? If I have indecomposable non-irreducibles, I have this stuff going on off the diagonal. I need to capture some information about that. And that's what I'm trying to do. And this stabilization of the SOCL in conjunction with the radical allows me to do this. So in Miyamoto's work, he has a bunch of red words. He has the level in GeoAlgebra, you're reducing it level in. I don't want to talk about, well, I might talk about a little bit about that. He has some map that is based upon this, and you get a basis. The main thing is that you get a basis, this basis that stabilizes. So anytime I have a weight preserving module map, and I restrict to one of these weight spaces, then I'll have the action of this on the SOCL. If it is weakly interlocked, then the action on the the algebra mod, the radical, will have the same linear operator. And he claims that there's a basis, this B, such that anytime I write down one of these operators with respect to this interlocked property, I have some duality between these pieces, and this B is stabilized under a change of variables that respects these properties. And then I'm going, so there's a bunch of words that I'm not gonna, the purple words, some of the purple words I'm not gonna explain too much. But if I have this setting where I have this duality here and this stabilization with respect to some basis, then I can take the trace to be this upper block B here. And what I do is I form the graded pseudo-trace, he calls these. And here I'm just taking my weight preserving map. I'm writing it with respect to some basis here. I'm taking this upper stabilized piece with respect to change of basis, and I'm taking the trace of that. Now my L0 may very well be, and usually would be, acting via generalized eigenspaces. Not eigenspaces, it's no longer semi-simple, so I need to split it into semi-simple and nilpotent parts. And this nilpotent part, so the semi-simple part, we're acting on weight lambda here. I'll get a q to the lambda then for the semi-simple part of my L0. And then I'll have some nilpotent part left over where I'm going to have to take a trace, take a q series expansion of this, and I will get thus log q here. And I will get naked taus in my pseudo trace. So that's the name of the game. Questions? Comments? Concerns? This is too complicated for most people to do. Okay, the drawbacks are. What?
All those pi gain?
We don't know.
I don't know.
We don't know. I don't know what.
Find a symmetric function?
It's some symmetric function, yes. And the abstract theory tells me that if I have C2 cofinite, then my J algebra is a Frobenius algebra. It has a symmetric function for which you can write down this bilinear form that stabilizes this, and you have this picture. Supposedly. We only have one really concrete example where we could even try this. So, okay, so trying to get around this. For one thing, it's a problem to construct these higher level J algebras and try and systematically understand modules using this. This is extremely difficult. And I know this because my name is as co-author on most of the papers about this. So, and I don't know, I can't tell you, people come up to me, how do I construct the higher level J algebra, such and such. I'm like, I don't know. And so these people have another, something called a mode transition algebra. That is a fancy algebra that also tells you things about smoothing of sheaves of modules of VOAs over pointed curves when one has certain properties. And they proved a conjecture that I had with one of my former postdocs on what are all the level NGU algebras for the Heisenberg. And so we do know all of those. Before that, we knew either level 1 J algebras or 1 level 2 J algebra. Now we know them all for the Heisenberg, and there's a new paper, should be out soon, where we do this for the Weyl vertex algebra, beta gamma ghosts. We can say what all the J algebras in that case are. And these are very special cases in which in all of those cases, the level 0 J algebra tells you everything you already needed to know. You don't even need the higher level ones, but it also tells you something about the smoothing of modules for these operators over these curves. Chris.
Were there mode transition algebras? Were they isomorphic to these? The Dimi, I don't know how to say your name.
Gibney Krashen. Yeah.
Were their algebras the same as the higher level algebras, or
So you see the higher level Jou algebra inside their mode transition algebras, or mode transition algebras give you more information, in particular these geometric properties. It is not, there is a question as to whether their algebras are the same as Ija Huang's A infinity. So he tried to put all the, you even have some problem with the Jou algebras telling you everything about the representation theory. So he made an even larger algebra, Ija did, and I think it's now been definitively said that the mode transition algebras are I don't know that they sit inside Huang's algebra, but they don't give as much information. But they're still handy gadgets. We use them to, calculate all the Jou algebras for the beta gamma ghosts.
But presumably, based on the result, are the mode transition algebras somehow easier to understand than the.
Yeah, I think it's, I mean, certainly for these, but these are free field algebras we're using them on, and I'm not sure, from a representation theory side, they're that interesting. Anyway. Okay. Yeah, I don't know how to determine phi as that. Only applies to the C2 cofinite setting. Okay, those are the problems. So the other approach that we had was just in some instances, like for instance, the C2, oftentimes in the C1 cofinite setting, one has like the Heisenberg or the Virasoro, not a great algebra, but it's not terrible. I mean, it's just pseudo-traces X. So I can define this notion of, in this case, I have much more than just weakly interlocked. I have this just single chain of modules sitting inside each module. So when I have this setting, you had this with C adjoint X with my modules U upper J. If I have this setting, in our cases, for the in specific cases, one can, for any degree preserving module map restricted to one of your weight spaces, have a block decomposition. So anytime I have this setting of 2 right here, I will have such a decomposition of my linear operator. It's just a question of then whether under a change of variables that still has then this decomposition, one stabilizes B. We do have situations in which B is stabilized. This is again the Sokal acting, this is your module mod, the radical acting. And if you have the situation where you can stabilize B with respect to a change of basis, then we can just follow Miyamoto and say, call the trace of this guy up here, the trace of the pseudo trace of this thing. That's what I'm doing right here. So call the pseudo trace of this mode, and then we put these into some generating function for all of the weight levels. Okay, so you can play that game. And we can prove in this setting that these are symmetric, linear, they satisfy the logarithmic derivative property. That was the first ingredient that you needed for Jou. So like I said, we get all indecomposable modules for the Heisenberg VOA, satisfy this, and we can do this for the universal Virasoro if you have a generic central charge, meaning that your C and H are outside of the Katz table, or you're inside the Katz table and your central charge 1 or 25, and you're inducing, for instance, a 2x2 conformal block. If you induce that, then you will get one of these strongly interlocked modules that has stabilized under change of bases. So these are settings where we do have all of this going on. And again, the reason is that anytime I'm inducing from one of these modules that has this strongly interlocked property here. There's only one unique symbol, which is the quotient for all of these guys. That's this guy, and these are all interlocked with each other, so I can always write my operators in terms of this matrix structure with a stabilized upper corner and a well-defined graded pseudo-trace. Inducing here, I really am just inserting one of these guys, this K by K Jordan block that tells you how, for the Heisenberg, it's this X right here is the X sub 1 that I wrote in our module. It's the ground state of the boson. For the Virasoro, universal Virasoro, this is L minus 2, generating again your entire module. And so you have, for your positive wave modes, you have a PBW basis, and you have Shapovalov form for the Virasoro, or the corresponding form for the Heisenberg gives you a one-to-one correspondence between how those modes are acting. So if you change a basis, you could stabilize that matrix form with respect to that.
Could you say once more what the strongly interlocked property is? Is it like the socle is the maximum?
It is exactly just generalize this. So I have just one chain of submodules. All submodules sit inside a chain of this form where each one of these has an unique irreducible quotient. That's strongly interlocked. All Heisenberg indecomposable satisfy this.
Okay, but also you don't need an ISO between like the head and the socle or something.
You do, and that's this weakly interlocked thing, and you do have this in this setting. Yeah, because of this unique irreducible, right, and a unique maximum. So the problem here, here's what is this tilde? So for the Heisenberg and for generic central charge for the Virasoro, this tilde is nothing. You just induce, and you always, when you do this induction, you don't get any singular vectors. But we know that for central charge, if you're in the Katz table, you have some singular vector. And so the reason that I don't get all Virasoros here, even though I'm inducing this way, is in this induction functor, I kick out any singular vectors, any vectors that don't survive if I lower them to the 0 level. And that's why I have, outside of generic central charge, when I do have singular vectors, it only happens when central charge is 1 or 25 that the interlock property will survive. And you don't have, for instance, in your simple, you have, the simple, you have to kick out a singular vector and all of its descendants in order to keep this simple. And you have to, it's a differential equation. It's a differential equation that it's the Jacobi formula between the determinant of a matrix and the trace of the derivative of the determinant of a matrix and the trace of a matrix makes a condition here on what the central charge can be. Because this modding out doesn't necessarily preserve this strongly interlocked property. That's what's going on. What was your question? I forgot what it was. Did I answer it?
I think you said when you explained what the strongly interlocked.
Okay. Oh yeah. Okay. Oh yeah. So I said this words, right? Okay. Okay, if I have this commutative associativity and I do a change of variables, so I've made some settings that are outside of the Zhu and the Miyamoto setting, in which we have C1 cofinite VOAs, and we have these graded pseudo-traces that are symmetric, linear, and satisfy the logarithmic derivative property. What do I do with them? I want to go to step 2, which is Zhu reduction. I want to do look at commutativity and associativity of VOAs, of correlation functions, and a change of variables. So this is key, and I'll draw a picture in a little bit. So when I have a VOA, I have, there's some variable here. Well, what happens if I change this variable? And I can always do a conformal change of variables for a function vanishing in a neighborhood of 0 or in a neighborhood of infinity, I could do as well. And I can change the vertex operator with respect to that change of variables. Okay, I have some weird thing happening here, but I will get, and in this case, I'm doing a specific one, e to the z minus 1, which goes from the cylinder to the disk. Then I could write down a new vertex operator with respect to this. So these are these square modes. And Zhu was the first one to realize, oh, I do get these isomorphic BOAs. And then in general, Huang did this for a general change of variables, and I did it for super conformal change of variables. So this is just a game you can play. And it so happens, so here is a taste of, if I have these things, the types of transformations I get out. I go from 2 modes to 1 mode on the cylinder plus some Eisenstein series. But it's called G reduction because I'm going from 2 modes, a 2-point function, to a 1-point function. And I'm getting these natural transformation properties that have Eisenstein series. Again, if I take a logarithmic derivative, it relates to my L-2 operator and Eisenstein series. So this is the type of transformation properties that I will get out, not just if you have rational or C2 finite, or you always, as soon as you start off with a symmetric linear map, trace-like function, these will pop out. So it's not something rational conformal field theory has. Okay. Now going after that to see what happens, you may have some hiccups, right? So going from Zhu reduction, you need to have, yes, you get some differential equations and stuff like this. And if you only have a finite number of these guys, so Zhu reduction gets you down to a finite number of these guys, and then these differential equations are much more easy to handle and figure out what space of functions you get out, but you can play that in any situation. And so for instance, and this was known a long time ago, Don Mason and Nagatomo saw that, okay, if you just do the 1-point functions for one free boson for the Heisenberg, you don't get modular invariance because E2 hangs around. But that's the only problem, is that you don't kick out E2 and just get E4 and E6. These are the Eisenstein series. You don't just get E4 and E6. If you just got E4 and E6, then you would have modularity. The E4 and E6 span the space of modular functions. E2 sticks around because the mode for the boson, it has an E2 in it. So you get pseudo-modular functions instead of modular functions. No, they're not called pseudo, quasi. They're called quasi-modular functions. This is the space of quasi-modular functions. So there's an example. We can show that you still have this property with the pseudo-traces. So as soon as you know your vacuum level pseudo-traces, which we have, this is not online yet, it will be soon. The vacuum pseudo-traces for the boson are online. Then you have complete control. So these are just, depending on what size Jordan block you want to take, you will get some polynomial in tau here. These will just be finite polynomials in tau. Okay, there's some work by, this is a graduate student, she's graduating this year, a student of Jeff Mason's. He's retired, but he has a student, I don't know how that happens, but she's lovely, and she's did this for the overfold VIs, where you have a little bit of trouble with G reduction to get down to the space of the functions. We can start to analyze stuff, sure, fine, that's what we're doing. Oh, and then, so a lot of times what you do to figure out what space of functions you're interested in is you'll spectral flow, right? That maybe your module category that you're taking is not itself the category that you want, maybe it, so for beta gamma ghost system. So for instance, for the beta gamma ghost system, it already has, so it's level 0 G algebra is the bio algebra itself, which already has non-weakly interlocked modules. So you have no hope of pseudo-traces, but the standard space of modules that you would take is not closed under modular invariance. It's not about modular invariance. So what is done in that case, and in cases like SL2, one uses spectral flow to enhance your category of modules. And under spectral flow, you end up getting enough modules. And here you have, in beta gamma, you have infinite weight spaces and everything, but we always take what are called weight modules because there's a Heisenberg running around and it grades your space as well. And so with these two gradings, you get into a finite weight space. And so you can doubly grade things and look at the doubly graded pseudo-traces. And under spectral flow, you can prove that if spectral flow is invertible, which it is in almost every case that you're interested in, then this property of weakly interlocked will be preserved. So if you're not going to spectral flow yourself into or out of the situation, in other words. So that's a fact. Okay, why does all this work? Can I say why it all works? Yeah. Okay, good.
We ought to start it a bit late, right?
Yeah.
So you do have a quarter of an hour or something.
Right, I'm doing okay.
Yeah. But I don't know how much you've left.
Okay. So what do I mean by change of variables and what do I mean by weak associativity and stuff? So what I mean by a VOA is just an algebra governed by world sheets. This is just Wong's 1990 picture, if you will. So I have to every, and this is, again, I'm just looking at the VOA itself rather than intertwiners, but if you want to think of intertwiners, you can as well. I have a pair of pants giving a specific one up to conformal equivalence, where I have just the actual Riemann sphere itself with the standard local coordinates vanishing at the punctures. That's what is functorially giving me my vertex operators. I have this action of the Virasoro that naturally arises because in general, I might have not a so nice data at the puncture local coordinate. It may have some modes changing it from the standard one here. But these can always be written in terms of infinitesimals, and these infinitesimals are what are giving you your representation of your Virasoro algebra. You have a determinant line bundle that's giving you the central charge. I can recover in this picture, this conformal equivalence is exactly just logarithm on 2 pi I that's reconstituting your tube. This change of variables that I'm doing is, so the moral of the story is your vertex operators. So the Riemann sphere picture is very, very handy because we can actually solve things there. So you can, if you sew things into each other, you can uniformize because you're uniformizing back to the sphere itself. So things like normal ordering under sewing works out very, very nicely. So you want to work on the Riemann sphere. When you're looking at some of these number theoretic invariance properties, you want to do a change of variables. I mean, number theory takes place on the cylinder or the torus, right? So you want to do a change of variables and relate it back to the torus. The change of variables that we use here is just slightly different. It's kind of interesting. When I have just one module, then I want this change of variables. If I have more than one module, if I have intertwiners, it's a slightly different change of variables that will allow me to see some of the nice number theoretic properties. remember that no matter what change of variables I do, these guys are going to be isomorphic as long as it's a conformal change of variables vanishing at either the 0 or infinity. So I can, the modules here are, and their Q series are going to be stabilized under this. So it's just a gimmick to be able to see what's going on. And so for instance, if I do this change of variables, then these certain sums of iterates for the usual modes relates to this P function, which is basically a version of the Weierstrass P series, if you know number theory. So it has interesting number theoretic properties. And so simply from this change of variables, for any VOA, I get this formula, okay? We know that for VOAs, if we take these three-point functions, then these all give you the same, they are the same analytically continued rational function, meromorphic function with poles at Z1, Z2, and Z1 equals Z2. They give you the same function. They're just, when we write down vertex operators, we expand them in different domains. So these are all the same. This picture was the original, this is where string theory came from quantum chromodynamics. They wanted to have two different Feynman diagrams be the same, and if you fatten them up, you got, they realized it worked, and so the string theory was invented by just fattening things up and drawing this kind of picture that would maybe show associativity. Of course, if I write this down in terms of the actual operators and their expansions, I get kind of an ugly formula called the Jacobi identity. So if you're an algebraist and you open up a VOA theory book, you'll see this thing. If I were to take, so these are these operators expanded in certain directions for Z1 and Z2. If I took residues of each one of these to pick out coefficients of all of these, then I can write this in terms of contour integrals for certain contours. This is a joke. This is the way you want to write the Jacobi identity if you're an analyst. Why are you laughing back there? You're laughing at me. What? This is not a path integral. This is a contour integral. This is all I have done. Oh. Don't ignore that. I meant contour. Here, that's why they're laughing. Path means contour in this context. I'm just using Cauchy-Riemann. Okay. Yeah, thank you for the joke. It was put there for you. Okay. Right. So so anyway, I can relate, one of the things that this says is that I can relate the commutator to modes multiplying each other by some iterate. But I want to use the path integral approach, and then I can integrate this P function that I get, and I can, writing my change of variables with, sometimes I'm going one direction, then sometimes the inverse pops up, but that's okay. Then I can prove that this difference, and the only reason I'm writing this down is that this works for any VOA. Then by doing this change of variables where I have gotten this P1 in this case, for a certain contour integral, I have this difference of correlators is equal to this guy right here, and I get, and this is just -1, and there are even no operators at this point. I've only just picked out these coefficients that came from my change of variables, and I'm using these contours, and that's where I'm getting the Eisenstein series. So it was shocking to me that, you know, because we're always in, oh, you have this certain type of BOA, you have this certain setting. This works for any BOA. And then after that, you know, so you get those formulas that I wrote up before, and then after that, you're just left to analyze how, you know, once I get to, that's me telling me that I have 5 minutes.
Okay.
I think my thing stopped now. So that I get some series, and then past that is just Eisenstein series. And this, so the moral of the story is, you know, as soon as you have world sheets, and as soon as you have fields and correlators that are governed by these world sheets, you naturally have this picture anytime. I don't know what I was going to say after that. Are there any questions? I could show you what some of the things are for bosons or the Virastoro, or I'll pause for a second to see if there are any questions. No? So for instance, here's the boson, one free boson done very carefully. This is, we did this for any, you have a change of conformal element if you want. There's a infinite family of conformal elements shifted by this non-quadratic element. And all of your indecomposable modules look like just your boson, maybe with the shifted conformal element. Tensor, this is just the vacuum space. This is the things that if I lower them, you get 0. So that's what all your modules look like. So when I was saying that they all come from the level 0 geoalgebra, is exactly this. I just insert some larger vacuum space than the one that you wanted, then just see the vacuum. And I induce by acting on this by all the raising operators. That's induction in this case. And so I get all of these, and this is exactly my Jus algebra. So this vacuum space really does look like C adjoint X mod these guys. And I can just calculate, I don't know what's interesting. They're all strongly interlocked. They all have, are invariant with respect to uniform change of bases. You have this interlocked property just from here. These are just the ones induced from C adjoint X. So you have all of the structure. You have your 0 mode for, so this is the 0 mode for alpha -1, the generator for your one free boson. And so it's acting like this. And I'll use this notation to separate into semi-simple and nilpotent part. And so your L0 operator is this guy. I might have this change with respect to some parameter. And so I get this as my L0. I get a semi-simple and nilpotent parts. And you can calculate your graded pseudo-traces. I get these log terms times my vacuum pseudo-trace, my vacuum pseudo-trace. And so, oh, these are the vacuum pseudo-traces. I get this polynomial times my actual vacuum trace. These will vanish for certain of your modules. So you can have modules, even just for the Heisenberg, where all your pseudo-traces are going to vanish if you choose the conformal element to correspond with your lambda for your Heisenberg. So they you know, and for certain modules they could vanish. And so these are some of the, for instance, series that you get out of here. Trying to understand, you know, what differential equation these satisfy, and so how are you expanding your quasi-modular form? So we have the space of quasi-modular forms times these tau polynomials.
No, pseudo-trace form is always you take a top form.
I mean, for me, pseudo-traces like use a Stalin trace for algebra centralizing your VOA.
I don't know what those words mean. But we
So
can-
given a module, there is always, I mean, of course you can write usual graded trace
Right,
and you take, but pseudo-trace is also unique for you.
but what?
Is it unique for you? Pseudo-trace for a given module?
Yes,
It's unique for you.
yes.
Because for me, it's not unique. Right, Inga?
I mean, I had to, so here I've just given you the ones for the vacuum. You know, I have all of the machinery of where I use these properties to get, for instance, here, let's just go back to here. There's a lot of work. Let's just go back to this result. There's a lot of work in here, right? To show that for any V, the trace for any V is in this space. And in fact, there's more. You can prove that you exactly get this space.
Mhm.
That you get all, you don't just get wind up in quasi-modular forms, but that you get all of them. That for one free boson, it is exactly the space of quasi-modular forms. I guess I didn't exactly say that there, but that is true. But it's stuff that I have not shown you, that I use these properties to, this is Jus reduction, to reduce any graded pseudo-trace for any module and element of your VOA. I don't know if that's what you meant. So if, yeah, for any element of my VOA, I have a different graded trace or graded pseudo-trace. So it's the Jus reduction here that is used to rewrite any multiple modes in terms of just your one mode, and for instance, for the Heisenberg to get any graded trace. And here, their work actually was just for V. So I guess I should go to our work. Oh, here. So this is for any module and any V. I wind up in here. So I wind up, and in fact, I again, of course, if I did up there, I get all graded pseudo-traces, but then I have a space that is multiplied by some polynomials in tau.
Yeah, but what I was saying, like there's a different point of view. You can, instead of different doubles, you can take one, at least it's a cofinite case, projective generator, huge. And then you look at the algebra of endomorphism of that projective generator, the intertwiners. It's finite dimensional algebra.
Right.
And then it has a bunch of symmetric forms.
Right.
Then choosing symmetric form, I can recover all your traces.
Right. Right. So this.
But also given W, it can be kind of big enough. It might contain in some sense several pseudo traces. But I think what you're defining, you take action of zero modes and you look at the most off diagonal block. Right, because
for the pseudo traces.
Yeah, for pseudo traces.
Yes.
The most of diagonal block, and you take the trace of that. This I would say top form.
I see.
Pseudo-trace.
So you have intermediate pseudo traces.
There are intermediate ones, yes, corresponding to the structure, because like in your example, I think it's like Cx over Xn, right, in the Morse ring. It's the self-extension of Heisenberg Fock spaces, right? Your example.
Yeah.
Right, so it has length n. And
Yeah.
in the Morpheus ring is n-dimensional algebra. So I would associate, there are intermediate, right? There are intermediate pseudo-traces.
That could be.
Yeah.
Okay. For these, we get these.
Thank you. I basically.
I'm done. I will be done.
Thank you very much. And more questions?
Do you need to solve some problems of convergence in your theory?
So for this, you know, in general, yes. So in general, especially if I go outside of these C1 cofinite settings and everything, to in particular prove that you're getting the entire space of quasi-modular forms in our case or something like this, one does need to be careful about what differential equations one is solving. In our setting of, for instance, the Heisenberg, we don't need to do this. It's just enough to have the Q series.
More questions?
Does E2 create problems for you on the conceptual level? I mean, E2 is either modular or holomorphic. There are these two variants. So is
Right,
there
I
some
mean,
meaning to
it's
this?
called, in the literature, it's called a quasi-modular form, which I guess is not, it's not so easy to write down the actual transformation properties. But no, I mean, I think it's perfectly fine. And one of the morals of the story is that, I mean, it depends on, yeah, what context you want it for, but one of the morals of the story is that you have some finite number of, well, if you have like a strongly finitely generated BOA, you have some nice set of modules, you have only some finite number of problematic fields you might have to modify your space by. But then after that, all you're getting are polynomials in E2, E4, and E6. Yeah. So, I mean, yeah, it depends on, is E2 a problem for you?
Well, I know that sometimes the fact that E2 is not modular, but or not holomorphic, that's the origin of anomalies in string theory. So it has very interesting consequences.
We would agree.
More questions?
Can you say something more precise about S-matrix section?
About what?
Modular action.
The modular
Z on these traces. In Heisenberg case.
Yeah, so these, I do, everything is modular except for the piece where the E2, and then E2 is not modular. It has this property of being quasi-modular, but that's the spaces.
On the question, so if I do tau goes to -1 over tau, can I then rewrite the pseudo-trace as a
Discrete sum or
like as
what?
an integral with something? Is there some concrete formula for this?
Yeah. I think that this is, well, just for the, we have not done this in our paper. From the, maybe it's work of Mason and Toot. They do this, I think.
Or Virasoro also? You wanted to say something?
The
about
Virasoro is much more complicated. So far, we just have that. I mean, again, for the Virasoro, we computed the level 1 Ju algebra. That is already very complicated. Just the representation theory of that commutative associative algebra. And so in our paper, we are only doing what you get if you induce from level 0. And so we get this interesting situation where it picks out, C1 and C25 and says you at least have a 2x2 conformal block that you can induce and you can have a well-defined graded pseudo-trace. And in that case, you just get the vacuum trace is just a single tau, power of tau with some coefficient times the vacuum trace. That's all it is. It's not a good idea to try and study the Virasoro algebra using Ju algebras, though. I mean, like you don't want to, even at level 2, level 1, inducing from level 1, like I said, I mean, the algebra, some of the modules are very nice, but the level 1 Ju algebra for the universal Virasoro is that.
A level 1.
Level 1. So you could,
quite right.
right, so you could start inducing from level 1 and see what you get, but.
Sorry, would you mind, what is level 0 then?
CUX.
It's just CUX.
Just
Okay.
components.
Oh, yeah, that's right. Yeah. The
You
same,
know its number,
the
right?
same
It's
as
irreducible.
Heisenberg, yeah.
Yeah, same as Heisenberg, yes.
Okay.
But Heisenberg tells you already about
So,
general blocks.
but yeah, are the quotients from level 1 to level 0? So
I
how
propose,
this
yeah,
algebra related?
postpone technical discussion of Zoo algebra to break. We are a bit behind, maybe 5-minute break, and we continue 10-2 with 2 short talks. So let's think.
Oh, yeah.
Let's
And
begin.